Hi. So this particular video is going to be about sound waves. We'll talk just a little bit about sound waves. And I'm going to start this out by asking a question. If you scream in space, can anyone hear you? Um, okay, we may know the answer to that question already. Do you recognize the reference? That's a reference to Alien with Sigourney Weaver. Ridley Scott was the director. Anyway, if you scream in space, can anyone hear you? The answer is no. I've got what looks like a link to a video there. It says experiment. That link takes us to a video that shows a bell inside of a glass container, and a vacuum pump is hooked up to that glass container. And the bell continuously rings, and we pump the air out of that glass container with this vacuum pump. And as the amount of air inside of the container decreases, that sound gets dimmer and dimmer and dimmer until we can just barely hear the bell. And probably the only reason we can still hear the bell is because of the fact that it's sitting on a stand, and the sound waves are transmitted to the stand, which sets other things vibrating at that frequency. I can't show the video here in this video, but what I can do is put a link in the description of this video so that you can see that if you want to. All right, so if you scream in space, can anyone hear you? The answer is no. Why is that? It's because sound requires a medium in order to travel. Now, typically we think of the medium of the medium for sound. We think of air. Sound travels through air. Well, sound also travels through liquids and solids. I know you guys have experienced, well, at least most of you guys have experienced sound traveling through a liquid because maybe you've been at a pool and you've been under the water, and you can still hear sound underwater. It's distorted. It doesn't sound right. It doesn't sound right, but you definitely can still hear noise. Not only does sound travel through liquids, it travels through solids as well. Let's see. We'll take a look in later videos, later material, at the relative speeds of sound waves in those different materials: liquids, solids, gases. All right, at the end here, I ask, are there any waves that do not require a medium? Light. Electromagnetic waves do not require a medium in order to travel. Which is good, because honestly, what's the number one source of light? It's the sun. And so the sun gives off light. That light travels through space, reaches Earth, and provides us with all the energy that we have. Whether it's we're getting it from solar panels, or whether it's the energy that's been stored over millions of years that now we use in some other form. But yeah, okay, so light waves do not require a medium in order to travel. We'll deal with that much later on. For right now, let's talk about sound. So I would like us to imagine that we've got a speaker, and we've got a tube there that we basically got that speaker on the end of. So you can see here the drawing that we have, or the picture that we have from this. It's not highlighter. There we go. Got this picture right here. So basically, we've got a diaphragm there of a speaker, and I don't know if you guys have ever watched what happens with a speaker with cover off, but you've got a diaphragm there that's pumping in and out, and it vibrates at the frequency of the sound that's being created by your electronics. So at any rate, we can picture this diaphragm vibrating in and out. And what is it doing? When it pushes forward, it's compressing the air molecules that are in front of it. Okay. So it creates this bunched up region there of air molecules. Locally there, the air pressure in that region would be higher because, well, there's more air molecules there. And then what happens? It pulls back. This diaphragm pulls back. And so it pulls back there. There it is, pulling back. Well, what does this mean? This creates kind of extra space there. and it's extra space, and all of a sudden we don't have, you know, we didn't have a space, and now we do have space. And it's like, well, we've got extra space for the air molecules to be in. So on average there, when this pulls back, it's going to create a region where, you know, there's much less density of air molecules. Let's see, less density of air molecules, that means lower pressure. What happens as a result of that? Well, some of these air molecules that were bunched up right here, now, okay, this pulls back, and we've got an area of low pressure, and those air molecules will rush back into that area of low pressure. And then this pushes forward again and makes those air molecules move this way, pulls back, air molecules move back, boom, 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 so on and so forth. So the motion of this diaphragm in and out causes the air molecules in front of the diaphragm to move back and forth, back and forth. Well, what happens when those air molecules move forward? Well, sometimes there's a collision that happens. They'll collide with another air molecule and cause those air molecules to move forward. And then when the diaphragm pulls back, some of those, you know, air molecules that are right in front of the diaphragm will go back into an area of lower air pressure. They'll create a void where they were, and an area of lower air pressure. And so the ones in front of that will pull back, and so on and so forth. So when we picture what's going on with these air molecules, what we should see, or what we should think about, is that these air molecules are really vibrating just back and forth about some equilibrium position. So it's not the air molecules themselves that travel in a bulk fashion from one place to another. Instead, it's pressure waves, it's variations, local variations in air pressure that travel from one place to another. The air molecules themselves are the medium. They just vibrate back and forth, back and forth, back and forth. This is really similar to the slinky that this shows on the screen, where we end up with bunched up regions right there, and regions where we really don't have many springs left at all, many coils left at all. So let's see, what kind of wave is this? This is a longitudinal wave. So sound waves are longitudinal. So the medium, the oscillations in the medium, travel parallel, or actually not travel, move parallel to the direction of our sound wave. So that's, if we remember, that's what a longitudinal wave is. It's a wave in which the medium, the vibrations in the medium, are parallel to the direction of the wave travel. All right. Let's see here. That was a lot, but let's move on. See what we got. Or let's try to. Okay. So let's see, if I let my diaphragm go for a while, you know, at a steady frequency, what I will see here is that I've got bunched up region there, bunched up region there, bunched up region there. The distance between bunched up regions is the wavelength for my sound wave. And then let's see, I could also maybe pick where my minima are, right there and right there. That would also be equal to the wavelength for my wave. It's a little easier to see the bunched up regions though, and kind of pinpoint the middle of that. And again, this is really similar to our longitudinal wave on the slinky, where we go from bunched up region to bunched up region, and that is a wavelength. Okay. All right, so the next thing I've got is a question for you. So here we've got a particle of dust floating in the air. It says it's about a ½ meter in front of the speaker. The speaker is turned on, producing the worst music ever. It's just a constant tone. It's 226 hertz, something like E, something like that. You can look up that sound, that, you know, that frequency yourself if you want to. Anyway, the speaker is playing 226 hertz. Which of the following statements correctly describes the motion of the dust particle? Does the particle of dust oscillate left and right with a frequency of 226? Does it oscillate up and down with a frequency of 226? Does the particle of dust move towards the right at constant speed, or does the particle just stay motionless because it's not affected by sound waves? So pause the video, think about your answer. Okay, the correct answer is A. So these air molecules, as they're vibrating back and forth, bump into adjacent neighbors and set those vibrating back and forth, and they bump into adjacent neighbors, set those vibrating back and forth. And some of those air molecules are going to bump into the dust and set it vibrating back and forth. So it is just going to oscillate oscillate back and forth, left and right. There we go. The one that I've got circled already, with a frequency of 226 hertz. Okay. It does not move to the right at constant velocity. It just goes with the flow of what the air is doing around it, which is vibrating back and forth. It's those vibrations, those variations in air pressure that actually travel to our air or travel to our ear, that set our eardrum vibrating, that allow us to hear. Okay. All right, one last thing here. How do we account for the differences in volume for sound? The larger the differences in the air pressure are between my condensations and my rarefactions, the louder the noise is going to be. So this is true in general. It says primarily it's due to this difference in pressure amplitudes. So I can imagine that right here, I've got my normal atmospheric pressure, and then the louder my voice gets, the more variation there's going to be in that pressure. Okay. So just like it says right there, my axis is atmospheric pressure, and then there's how high the pressure gets. There's let's see how low the pressure gets in comparison to atmospheric pressure. And the bigger those crests and troughs are, the louder in general the sound is going to be. Okay, there's something called a Rubens tube. I encourage you to look that one up on your own. That does it for this one.